Okay, it's my great pleasure to introduce Simon Scheidegger. He's coming from Lausanne. He's a real rising star in making important contributions in economics and computation and solving very high dimensional dynamic programs and models. And we'll see that today. He's very gracious because he's getting married soon and he's taking time out of his wedding preparations to come talk to us. So we thank you so much, Simon. Thanks so much for doing this, and you have the floor right now.
Thank you, John, and my pleasure to be here. Actually, it's a good distraction to not think of all the details I have to prepare before the actual event starts, where I get chained. No, I'm kidding. So it's a real pleasure to talk to you today, despite I cannot be there physically. I would have loved to. So what I'm going to talk to you today is two methods that I believe are pretty useful, as toolkits when solving and also estimating complex economic models, dynamic stochastic economic models to be precise. Just 2 words before I will start is for all I'm going to talk today, there is example codes. So like the first part of the, say the first 70% of the presentation will be on using so-called deep equilibrium nets to solve dynamic stochastic models. For this, we have a Git repository with models for will be, as you will see, it's mainly all overlapping generations models that we solve there. But like there's notebooks, there's code, so like there's plenty of stuff. If you like what you see today, go give it a try. This is joint work with Marlon Nocinovic, who just recently graduated from the University of Zurich and now starts a postdoc in the econ department there as well, and Luca Gegauf, who I'm co-supervising as a PhD student. And then afterwards, the last part, I will talk a bit how deep learning we believe can be useful also to estimate complex models. For this one, there's also a Git repository. Note this is a joint work with Antoine Didisheim, who's a PhD student of mine in Lausanne, and Hui Chen from MIT. Okay, so as John said, I work at the University of Lausanne and the Department of Economics with the job title Prof for Data Analytics, so whatever that means, but who cares? And there's also like on my website, there's plenty of other codes along the, like for solving and estimating models. So if you're interested, go and check out there. But okay, so what will be the roadmap? The program will be pretty packed. So what I will do is I will first give you a quick motivation on why we're doing what we're doing. Then I'll give you a quick overview of machine learning in general, but mainly also to put it in context with what you already may know from the standard econometrics classes that you see in grad school. And then once we have these fundamentals, we are ready to see what deep equilibrium nets are. So it will be a way to use neural nets with unsupervised machine learning to solve complex models. And then at the end, we will use deep neural nets to also estimate models. And as I said, throughout, so I will not have time to do this, but like for all the stuff that I do here, I put also to the Git repository of the summer school. I uploaded a bunch of codes. For instance, there is a code that explains how gradient and stochastic gradient works. So the way how to estimate the parameters of the neural net. There is also a complete introduction to TensorFlow. So this is well, it's a software provided by Google that we use mainly for solving these models. And yes, the other two repositories I already mentioned. But okay, so why are we doing what we're doing? So if you think of a lot of models in econ, contemporary models, they're heterogeneous. And examples for this would be overlapping generations models, right? So minimum model to study, say a reasonable, retirement fund or stuff like that, pay-as-you-go social security, etc. What you would like to have is certainly, a representative agent for. You have a different way of, consuming than when you're at your, at your peak or when you're retired, etc. And this is also implied by the data. I mean, this is a bit of an outdated income, but you clearly see, over the life cycle, the income changes drastically. And on top of that, you also have the, the distribution. So like if you would like to have a social security models in reasonable fashion, you probably would like to have like an annually calibrated model, but you would also want to have like per, one agent per percentile, just to make the example. And that's not all. Then stochasticity is missing. So like you may want to have aggregate shocks, you may want to have idiosyncratic shocks, etc., etc., etc. So you easily end up with, say, 60 times 10, so that would be several hundred agents plus shocks. So just by construction, to study contemporary question, your model is high dimensional. And on top of that, there's other constraints that this model face, like, these agents you may want to impose also borrowing constraints within these models. So like the models are also highly nonlinear on one hand side due to shocks, like a COVID shock, as you have seen just now, or also like if you have like financial constraints. So you have high dimensional stochastic models, and the policy functions that you want to look for, they're highly nonlinear. So more formally, if you then write down your equilibrium conditions, this is what you typically would do, right? So you would write down your first order conditions, you would have a state, and then you have some law of motion, and you would, say for simplicity, if you had a one-dimensional model, just one state variable, so you would then discretize, your state, say with 10 points along one axis, and then you solve 10 times a nonlinear set of equations. Okay, but then you have two states, say you have two agents, then you have 10 times 10 equations to solve. That would be 100 equations. Then you have three agents, you have 1,000, etc., etc., etc. So this is called the curse of dimensionality. This is really bad. So like you cannot beat that. So if you just use the naive grid-based approach to solve a model after 3 to 4 dimensions, you're just screwed. And then there's other problems that we often face in economics. So we want to find a global solution to our model, but the ergodic distribution may not be even on a hypercube. So there's plenty of models. Here I'm making a rabbit, but so now just imagine the ergodic distribution of your model looks like a rabbit. So this also faces the curse of dimensionality, but on top of that, like most, say polynomial-based approaches, they require a tensor product construction. So they require you to work on a hypercube. But if you cannot map your model on a hypercube, you're also lost. Let me just go here to this example, and why is this a problem? So like then you could say, okay, let me be generous, let me map my hyper rabbit just inside a hypercube. And now let me just make a concrete example. So like, if you have a high-dimensional model, let's say we simulated, the ergodic distribution often looks like something like a sphere. So notice, I'm interested in the part of the model that lives inside the sphere. But now let's look here, 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 and here. If I use a grid-based method, I need to approximate the model there even if I don't need it. So this is kind of a waste in two-dimensional, but you say, okay, I could get away with that. But see, the ratio of the sphere to the cube, the bounding cube in 2 dimensions is 1.3. In 3 dimensions, it's already 1/2. So 50% of the computational effort you put is wasted. But now, if you want to go and solve a 100-dimensional model, the ratio would be 1 to 10 to the 39. So this is just an enormous waste of resources. That's another problem with high-dimensional models. And then the last one that I wanted to mention is, if you look here, so I said we need to solve, for instance, a set of nonlinear equations. Could also be the Bellman operator. But just to demonstrate what I mean with, what the curse of dimensionality implies is the following. So say we have one state variable, so 1 dimension, and say to solve one set of nonlinear equations, it takes 1 second, and say we don't have any parallelization. So solving 10 points would take 10 seconds. Okay, no problem. You press play. After 10 seconds, if you're not happy, you solve the next one. Or if you think of estimating the model, right? So you need to repeatedly solve the model. So like you have a loop and outer loop that probably estimates that. So this can take a few seconds, but fine. In 2 state variables, if you use Cartesian grid, so like this, solving with the same speed roughly takes you 1.5 minutes. So this, you press play, you check your email. If you're happy with the results, you're done. Otherwise, you press play again, you check your results. So 2 dimensions is already kind of cumbersome. With 3 dimensions, this translates to 16 minutes. So like you solve your model, you press play, you go and have a coffee, you come back, solution is there, you're probably not happy. You change some stuff, you go for another coffee, and after an hour, you're super nervous because you just drink so much coffee. You see, and this goes on. And then with 20 dimensions, which is far below what we're aiming at, the curse of dimensionality would translate to having run times 240 times the age of the universe. So like it just becomes infeasible. So what we want to have, obviously, is we want, from an abstract perspective, we want to have something that can alleviate, I'm deliberately saying alleviate the curse of dimensionality, because breaking the curse of dimensionality is a tricky beast to state. But like we want to have a method that can deal with high dimensional state spaces. It can deal with strong nonlinearities. So we want a method that can approximate policy functions that feature kinks, for instance. We want to have a computational method that potentially can also benefit from contemporary high-performance computing hardware, because as you will see, deep learning in particular can benefit from graphical processing units a lot. And then finally, we would like to have, a tool that can be confronted to data. And as I said earlier, the solution process is one thing, but like if you want to estimate the model, you also want to be able to, some sort of query a solution fast. So this is kind of the abstract requirement we have to tackle the problems mentioned. And I will get to the point, but the method that we designed here, deep equilibrium nets, deals with that relatively well. So it can deal with nonlinearities, state spaces. It can deal well with irregularly shaped state spaces. And the last thing is, as you will see, and this is really the cool thing, which I like most, we do need to implement a solver anymore, a numerical solver. So the training data, as you will see in a moment, can be generated just via simulation. So we don't need to invoke a nonlinear solver, but rather we just simulate the model, and then we use stochastic gradient to update the guess for our policies until convergence. So this is what I will, hopefully convey you in a moment. And then this is still introduction. So sorry for my, kind of extensive blah blah here. And then the second part, what I was just going to say, now we are able to solve a high dimensional model. Now we also would like ideally to confront our model to data, because in the end of the day, a model, what is it worth if it just describes nonsense, right? So while models are useful, I believe, we're just also bound to reality. And if the model cannot match basic features that we see in the data, it's probably not such a good model. So the second part of this deep structural estimation is the following. Since we can deal with very high dimensional problems, what we will actually do is we will also add to the state space the parameters as additional states. It's, sounds very trivial, and it is in fact trivial. It's computationally not that trivial, but like from a conceptual point of view, it's trivial. So we will have models that consist of the exogenous and endogenous states and parameters. And then we solve the model once with the neural net. And then we have something, engineering literature, this is called a surrogate. So that means you have the model solved, for all combinations of states and parameters. So thereafter, you can directly estimate the model because it's dirt cheap to evaluate it. It's just an interpolation in the end of the day. So like you can generate moments on the fly, you name any quantity of interest. So this really makes it, quite operational to confront then complex models to data, even if these models have a lot of parameters. So, okay, this was the motivation. Now, why neural nets? So like, we all read the newspapers. So what I want to convey you in the next, say, 15 minutes or so is like, I just want to somehow convey why I believe neural nets can be useful in economics if we use also a bit of the expert knowledge we bring to the table from our own side. So this is all, I'm skipping this, these slides, but like you have all read these headlines, right? So there is like deep learning is useful in drug discovery. Like if you look at reinforcement learning, they train models that can, outperform humans in video games, in Go, etc., etc. Then there is, for instance, like, if you use a deep neural net, you can train it to then generate music. So it's actually pretty fun if you go to this web page. So they just fed it with the basic tracks, and then it generates music that sounds alike. Deep learning was useful, for instance, in style transfer. So if you have Kandinsky, and if you have a dog, and you want to make your girlfriend the present, you can make, a Kandinsky dog. So it's also, if it's useful, it's at least like it's a fun thing. But what is probably more interesting over the last few years was the tremendous success of self-driving cars when reinforcement learning was applied. Color coding, coloring old movies, and even having robots walk around. So I'm not going to the details so far. So deep learning is not new at all. If you look at the history of neural nets, some first formulations were already presented in the mid 40s, actually when my father was born. So that's so the question is, why is it now emerging? Because as you will see in a moment, it's in principle just like a very flexible function approximation that neural nets can do. And I believe, and I mean, this is also I believe that the common view of most people working in the field, there's three things why neural nets and deep learning, emerges right now everywhere. One is the availability of data. The second one is the special purpose hardware that can evaluate, so train and evaluate neural nets. So that would be GPUs and TPUs, because as you will see, most of the operations that you perform on neural nets is matrix vector operations. So dense linear algebra is optimally suited for GPUs. And then finally, also, big software or tech companies, they make it easily accessible. So highly tuned codes like TensorFlow or PyTorch, they're all implemented in low-level languages, but they're all, are accessible to peasant programmers like myself with an interface to Python, for instance. So this, historically, is a very interesting point in time that we're in. Now, just, since I covered today a lot, let me just say, for those of you who thereafter are interested in that topic, there's a lot of, I would say, good and accessible literature. So one of my favorite books that I use also for my courses is Deep Learning by Goodfellow, Bengio, and Gourneville. There's a bit older book by Bishop. This covers machine learning a bit broader. And if you don't feel so comfortable with the mathematics that arises in machine learning, there's also, I think, a very recent good book, which is called Mathematics for Machine Learning. Okay, so let me now, in the next step, make a few links from, first introducing some basic terminology of machine learning, from which we then move on to deep learning. So there's typically, I believe, a bit in the daily life is a bit of a mix of terminology. So let me just put that straight here. And so when people talk about artificial intelligence, so this is rather the questions, can computers be made to think? So I'm not covering that today at all. What I'm interested in is just way more trivial. I want to focus on machine learning, which is a subfield of artificial intelligence. And what do I mean by that? So typically, like in ordinary programming, say if you want to solve something numerically, what you would do is you would have rules and data, then you have some algorithm, and that will give you an answer. So just think of, you solve partial differential equations, you would have your multi-grid algorithm, then you press play, and then it gives you the answers. The difference in machine learning typically is, for instance, in supervised machine learning, as I will discuss more in a moment, you have answers, and you have data. And what you will find is the rules. So talking of economics, given X and Y, you will find the map that connects the two. And then finally, deep learning is just a particular subset, a particular, tool within the realm of machine learning, just to put the terminology. And there's multiple flavors of machine learning. So there's supervised machine learning, where you essentially have X to Y. So you're looking for a map X to Y. And there you have two types of classification and regression. So you want to do prediction for a continuous variable, that would be regression, as in the typical econometrics exercises, or classification if you have a discrete value to predict. Unsupervised learning is rather unlabeled data. So you just have X, so say you have points, and then you want to find structure within that. And then the third typical flavor of machine learning would be reinforcement learning. And in reinforcement learning, what you then would look for is optimal policies. So this is pretty close or even identical with solving a dynamic programming problem. Just often here, you don't have a law of motion prescribed. And again, I think it's important to see that before we afterwards move on. So supervised machine learning, the baby example would be the following, right? So you have data, so that the red thing is data. So you have X and Y. And then what you do is you have a model, a hypothesis. So your model would be a linear model that has two parameters. It has parameter W and W naught. And what you want to do is you want to find the parameters that optimally describe the data. And you do that by minimizing some objective function, as you will see. So let me skip that one. Skip that one too, and directly go here. Now, the building blocks, as I said, so is X and Y for this sort of algorithm. So X in the terminology would be called the input variables or input features. The Y would be called the output or the target variables. Then in the language of machine learning, then you have the training sample. So you have a pair of training points. And you can also have the training set. So given the data, given the hypothesis, you want to find the parameters of the model. And those you determine by writing down a cost function. So as you will see in a moment, a popular one is for doing regressions, is you minimize the mean square error. And how you do that? So you have the cost function which sums over all samples. Here you have the hypothesis that is parameterized like this. Then you have the targets. And then you compute your loss function. And then you minimize this object to obtain the optimal parameters. And as you will see, with neural nets, it's the same game. The difference is just like you may have hundreds of thousands of parameters, but like mechanically, it's the same. So again, building a machine learning algorithm, very well, even, arrogantly speaking, consists of 3 steps. You choose a model hypothesis, a model that may be a linear model, maybe a polynomial model, or in our case, it may be a neural net. The next thing that I haven't touched so far is we need to define a cost function. Because when we come to economic models, this requires a bit of a clever way to do that. And then finally, we need an optimization procedure to find the optimal parameters. So in our context, that would be stochastic gradient descent, as you will see in a moment. So we need then computationally three things. So we need the data. So either we have them or we can generate them. And obviously, a bunch of linear algebra, statistic tools, and optimization routines. Now, with this general background, let's move on to neural nets. And this is a picture that you have all seen. Essentially, that would be, a three-dimensional input mapping to a two-dimensional output. So you could imagine, three state variables, two policies that you want to approximate. Now, what does this mean? So let's show you one by one what a neural net is, namely a universal function approximator. So the fundamental building block of deep learning is the so-called perceptron. And again, like this dates back to the 50s, where they had, made the connection to how a brain works. But like for us, just think of it as a very flexible or powerful function approximator. Say here on the left-hand side, we have the inputs, m inputs. So that would be an m-dimensional vector. So r to the power of n. And then we can weight these inputs with weights. So we have the inputs, we have the weights. So we add the two up. And then we activate that here with the function g. That would be an output. So that's all there is. So that would be the basic building block, the perceptron. And now there's something missing here, namely the so-called bias term. This one. This just allows you to shift this function to the left or the right. But so, at this point, there's not much difference than any function approximator. So it's just like I have y hat, and you could imagine, y minus y hat squared, something like that, would yield me the optimal parameters. But anyway, so I have this weighted sum, this nonlinearity. And let me just point you again here. So we have this vector matrix multiplication. This is one of the reasons why then GPUs are so powerful. So you will see in a moment, you have huge matrices, you have huge vectors. So you can really use the power of GPUs. But okay, so that's the first part. Now, what sort of G can we have? So historically, people were using the sigmoid function. It looks like this essentially. It maps something between 0 and 1. There's other functions. So like, it was shown that if you have deep learning, so like many hidden layers, as you will see in a moment, this is probably not the best activation function, but like you have sigmoid, you have hyperbolic tangent, ReLU, which is nowadays probably the industry standard. And as you will see in a moment, the important point about these nonlinear activation functions is that they have, they're differentiable. And why is this useful? As you will see, when we want to find the optimal parameters of the neural net, we need to know the gradient, obviously, because we want to optimize. Okay. Now, with that, we only had like a single output. Now, multi-output is obviously trivial to extend. So we had here the input on the left-hand side, but now let's have two outputs. So the only thing that changes, you can do the math on your own a little later. Essentially, sorry, here I need the color. All these nodes, they connect to all these output nodes for now. So you have just like the matrix with the coefficients becomes more complex. So you have 2 outputs, and you have 3 outputs, etc. But this is not a deep neural net. So what does it make a deep neural net? This again, we have the input layer, and here we have the output layer, but we start to add nodes in between, which are hidden. So like say you can observe here the Y, you have the input X, but these C's in between, this is a hidden layer, this you don't observe. So this would be a single layer neural net, but the mathematics is always the same, right? So to go here, you have this weighted sum of the input nodes. If you go to C1, you have again a weighted sum, activated, etc. So it's just like evaluating a neural net. It's just a gigantic sum in the end of the day. And now it doesn't stop here. So this is just like a single layer neural net. It's not very deep, right? So the superior performance over the last years in a bunch of applications particularly came because like people added a lot of the, so I'm just drawing these X's in between, but you could imagine here, like say we have here 5 hidden layers before we get to the output node. But it's mechanically, it's always the same. Just like you connect the dot to the dot. And so this is called the fully connected deep neural net. Now, you know, so I promised to John to mention this. So there is a bit stuff known why they are so powerful, neural nets, but in the end of the day, it's not too much from a mathematical point of view. So what you can prove is, like, so they satisfy universal approximated properties. So you can essentially approximate any Boolean function by a neural net with a hidden layer. But you may eventually require an exponential number of nodes in the hidden layer. So this is, you know, pretty useless if it comes to, you know, actually implementing that. So you need to do a lot of, you know, hyperparameter tuning yourself potentially. With continuous functions, you can also prove that, you know, every bounded function can be approximated arbitrarily small, but it doesn't with one hidden layer, but it doesn't tell you how to add, you know, how many nodes you need to choose in the end of the day. Nowadays, you know, there was recently some proofs, for instance, by Du Montanelli in SIAM. They showed, for instance, that the convergence rate given a certain neural net architecture can be bounded by sparse grids. And sparse grids, you know, are relatively well under control. In particular, like Bonn is the world center of sparse grids, so that they may confirm that. But so the problem is there's strong restrictions on the types of, you know, functions you can deal with. So they use a hypercube at the particular you know, like the magic within, you know, to prove that sort of things. It's not really useful, I have to say, for, you know, for the kinds of application in econ we have in mind. But at least it can give an intuition why, you know, in particular, deep neural nets can outperform other methods well. But what I want to mention here, I think at this point, and a lot of people working in the field would agree, here, you know, the computational frontier is ahead of the mathematical frontier. So when you work with deep neural nets in your daily operations, what you really have to do is, you know, verification, validation, and uncertainty quantification. So like you really, once you believe you have your model solved, you need to do a careful job with, for instance, computing ex post the Euler equation error along a simulated path. Just do a bunch of good robustness checks, because like just from the basic math, it's not clear if you have a certain architecture of the neural net that you're good. Okay, now before we go to the deep equilibrium net, just as I said, so in our application, we're at the moment interested in approximating functions, like we are interested in a regression type of problem. So for this sort of problems, the mean square error is probably the loss function one would pick. While if you want to do discrete values to predict, you would choose like a cross entropy error. Okay, now the training. So as I said, we have a lot of parameters in a network. Now, how can we find them? And we find them again, like by writing down the loss function and then looking for the arc mean of that thing. And this is done with some variant of gradient descent. And how does this work? So I'm just giving you the intuition. So you would say you have two parameters, just for simplicity. And then the z-axis would be the loss function. So what you typically do when you do gradient descent, you start somewhere, then you check for the gradient, then you walk downhill a little step size, then you recompute the gradient again, and then you eventually, go down to a local minimum. Obviously, if you would start over here, could easily be that you end up over here. So just like by this example, it becomes apparent that like these sort of methods, they work, but you're not guaranteed to go to the global optimum, but only to the to a local optimum. This also boils then back to what I said before. You may want to do a bunch of robustness checks on your solution. Okay, now hit the intuition, but how do you do that? So you have a lot of parameters. So you have a huge vector that describes your coefficients in your neural net. You initialize them randomly. Then to update those, you take the old parameter, you do a little change in the parameter, and you proceed with that until this change here is 0. So like W at tau plus 1 minus W at tau is roughly 0. So, and this is called the learning. This is called the learning in this game. So in neural nets, as I said, you initialize the weights randomly, say normally distributed. There's a lot of literature how you can choose those. Then you compute the gradient of the loss function with respect to the parameters. This can, as you can guess, that can be a tremendous computational bottleneck. Then you update the weights and you proceed with that. Now, just a bit of terminology. So the step size for that, this eta, it can be adaptive or it can be fixed, but this is called the learning rate, just to put it in the right language.
Simon, just in terms of time, we're a bit past time.
Okay, that's okay. I'm almost done with neural net. Sorry. Thanks. Sorry. So this is tremendously expensive to implement, to compute. So what you then could do is also you could be extreme, say, okay, instead of computing the gradient of the loss function just with respect to a single point, but this is obviously noisy. So what you would then do in the end of the day, it's called, batch gradient descent. So you take a subset of your observations, you average them, and you compute, the gradient with respect to the parameters like this. And then finally, this is also again why, to come back to why it's important to have, the gradients available from the activation functions is now, this is called error backpropagation. So at the end of the day, I need the gradient of the loss function with respect to the parameters. So we have J, and they would like to know, say for instance, J with respect to parameter 2. So that would be partial of dy times partial dy over d2. And this gives me the loss function. So this so-called error backpropagation, it's just an application of the chain rule. And to compute these objects, automatic differentiation is tremendously important. Okay, now let me move on. So I said there's a lot of more details, but I had to have this foundation first ready. There's a lot of more to know, and I have here all these bonus slides. There's a lot of stuff that one needs to know if you go to daily operations. And there's codes that they uploaded. And now, as I said, now let me actually start with the economics, or like with the deep equilibrium net. So as I said, we want to use deep equilibrium nets as a method to solve dynamic stochastic economic models with high dimensional state spaces, with strong nonlinearities, and which have potentially, well, also strong nonlinearities. So what it is, it's a method based on unsupervised machine learning, as you will see. And now let me go to the nuts and bolts of the basic ideas of deep equilibrium nets. Neural nets have a lot of parameters. And that means you need a lot of training data to find the optimal parameters. So we need a mechanism to generate data swiftly. So ideally, we don't want to invoke a nonlinear solver in any ways, because this is computationally expensive. So the key ideas that we use in deep equilibrium nets are threefold. So the first thing is we come up with a cost function that is economically motivated, an unsupervised learning cost function. And namely, it will be the implied error in the optimality conditions of our model. That's key idea one. Then once we have that, we use stochastic gradient descent to learn the equilibrium functions. And then finally, as I said, because we can simulate the model instead of invoking solvers, we can generate a lot of training data. Okay, so that was a bit blurry. And now let's get to the point. So when we typically solve, say, an overlapping generations model, what we would do is we set up our grid, sparse grid. So we have, for all the states, we have an upper and a lower bound. Then we solve the model at the iteration step, say 1. And then with time iteration, we update the policy given the previous iteration's solution. Then we proceed until some error criterion is satisfied. Generating this data, and this would be a typical supervised approach, right? You have X and you have Y, and then you approximate the function. So the data, or the way to generate data, is typically expensive, hence we have small data. So here is now the key innovation where we think, neural nets are useful. So what we do is we write down a loss function as follows. And this is really the most, how I say, this works for any model. I will then afterwards talk about the OLG model, but here it's the most generic way. So G would be the equilibrium condition, so the first order conditions of my model. We know they need to hold along a simulated path. So if I know the true equilibrium policy function, so given a state, that object would evaluate to 0. Now, what we do is the following. So we write down all the equilibrium conditions. That's the first thing. Then we initialize a neural net that encodes the economics. So say if you have 10 states and 10 policies, we have the input would be 10-dimensional, the output would be 20-dimensional. In between, we choose the architecture somehow. But the critical thing is we initialize the neural net randomly. So it's just like all the coefficients are initialized. So my policies will be just completely nonsense. But that's not a problem. That's the cool thing actually, because like what I then do, I have the dynamics of my model, right? So what I can do is I have a completely shitty, sorry for the wording, I have a completely shitty policy. Then I simulate my model forward, say for 10,000 steps with a completely shitty policy. This loss function will be gigantic, but we know by construction it needs to be 0. So what I do is like by simulation, I can generate, so this costs me 0, like generating this, simulating the, x1, x2, x3, and at each of these, at each of these states, evaluating the policies, just like it costs nothing. It's just like matrix vector multiplication. So it really goes on the fly. Then I update my policy. So the neural net in a certain step. So like once I generated these 10,000, observations, so to speak, I let the stochastic gradient do its magic. So it will adjust the policies such that, the error, it reduces. You simulate again. This will improve the policies, but the error will still be huge. And you continue until this thing is approximately 0. So this is the basic idea. Now, what does this algorithm look like? So as I said, so you need to choose, how many steps. You choose for, what is the error criterion. So for instance, if it's a unit-free consumption errors, which are typically, the Euler equation errors, you say, for instance, an acceptable level of tolerance is a maximum error of 10 to the negative 4 or 10 to the negative 5. I don't know. So you fix these errors. Then you choose your neural net. This is a bit of an art in itself. Then, as I just said, it would generate your training set. So you simulate, say, 10,000 observations, 10,000 states. You update your policy, gradient descent. Then you repeat until until convergence. So this is the basic idea. Now with that in mind, so this really it's very powerful. So we literally at the moment we use it in 6 completely different.
Just one question.
Yes.
This is very, very clear. I just had a question. In the literature on simulated method of moments, the idea is that you're minimizing over these parameters a simulated objective function. So it's similar to what you're doing here. And McFadden and others say you use common random numbers, because if you re-simulate with new random numbers each time, the objective function is very jagged, and so to kind of get stochastic equicontinuity, you want to use common random numbers. Is that also used in this approach in terms of the simulations and the training?
So let me answer part of this question now. The part of when we do about the estimation, let me talk about part of it later. So here, what we really use is just the law of motion. So like literally, what we will have is we'll have an approximation of the ergodic set. So we just use the policies and the dynamics implied by the policies. So we don't draw random. Well, okay. So here we have a Markov. Here we have anyway, a Markov chain. So we just take the dynamics implied by the model itself. It's different than, one could obviously also do, we just draw random numbers, then evaluate the first order conditions, loss function also there. But here we really just simulate instead of, doing random numbers in the sense. Is that what you asked?
Yeah, wonderful. Just a little visual thing.
Okay.
See this selector of your highlighter tool there, and sometimes it's hiding things.
Ah, okay, sorry. Okay, let me.
No big deal.
Better?
Great, thanks.
So, welcome. So now let me be a bit explicit with the baby overlapping stochastic overlapping generations model that you all know, just to be a bit more transparent. So, say you have an OLG model, agents live for 60 periods, is annually calibrated. So time is discrete. It's an infinite model, so time goes to infinity. We have one representative household per cohort. At every t, there's a representative household born. There's no uncertainty about lifetime. So people, they start to work with age 20, they die with 80. There is a exogenous aggregate shock C. I mean, there's multiple of those, but they follow a Markov chain. And then there's this strictly positive labor endowment, and this is just, it's not calibrated. It's just like to highlight the basic idea. So this could obviously be like a started, could be more complex, but doesn't matter for the sake of. Then you have the households, they supply the labor endowment inelastically at the market wage W. Then what the agents do is the agents are life maximized their time separable discounted expected lifetime utility. Then what you have is also the households, they can save 1 unit of consumption goods and then get a unit of capital good in the next periods. So you have essentially this transition from capital holdings today into tomorrow. Then there's a bunch of other standard assumptions, so households cannot die with debt. Then, to make it a bit more fancy, we have a borrowing, an exogenous borrowing limit to introduce a kink. Then you have the households, they sell their capital to the firm at the price R. Then we have the typical budget constraint. And finally, the agents are born or die without assets. So just principle of very simple OLG models. Then you have firms and markets. So we have a representative firm that we call Douglas production. Then we have, as I said, we have TFP shocks. And then we have depreciation shocks. And it's just like a Markov chain. So just forget about the numbers for now. It's just like one is persistent and the other one is IID. And then you have the firms, they maximize. And then we have stochastic production given by that one. So I need to go a bit fast here, but that's just like how it is. Then you have competitive spot markets. for consumption, capital and labor. So the equilibrium is described essentially by agents maximize, firms maximize, markets clear. So this just gives you a bunch of equilibrium conditions. And now how does that map now to our approach? So what we're looking for is the policies functions, or particularly we're looking for a functional rational expectations equilibrium according to the definition of Spear 1988, I believe. So we're looking for a function that maps, the state is C, which is the shock, and K is the capital holdings, maps the state into the policies. So we have essentially a mapping that maps the state into, like, 60 cross 4 maps it to a 120 dimensional state. So the policy that we're looking for is the capital investment functions and the KKT multiplier. So this is what we're looking for. So we have two types of equations. So we have the equality constraints and we have the inequality constraints. And now the cool thing starts with the neural net. So like the G, the equality constraint is what we stick into our cost function that we want to minimize. The law of motion we have, so like getting from a state today to tomorrow, is prescribed by this one. And then the inequality constraints, we don't have to worry at all. We can enforce this by the neural net architecture, in particular by choosing the appropriate activation. So here we have the policies lambda and R. They need to be bigger equal than 0. So we don't need to do any crazy stuff with the solver, but we just need to activate those with the soft plus. So again, let me repeat. So what we will do is we draw a combination of C and K. We randomly initialized the weights that parameterize these policies. Then we simulate forward with this prescribed law of motion. Then we have training data. Then we let stochastic gradient do its magic, update the policies, simulate again until loss function is close to 0. Now let me just show you how this then looks. So what we have here on the right hand side is randomly initialized the capital as a function of h. So this is obviously complete nonsense. And the cost function here is gigantic. It's almost 10 to the 8, but I don't care. Then I start to simulate. So after 100 times updating the policies, capital already starts to look reasonable, but the error is still like quite big. It's probably 10 to the negative 1 or so. Then I let it run a little longer. And then already after 7 minutes of really just running that on a laptop, I start to see on the right hand side, a distribution of capital, which looks some sort of something which is economically reasonable. But bear in mind, this is a 60-dimensional model with aggregate shocks. So this is not something trivial to show you, to solve usually, right? Then we let it run a little longer. Then so after, can be, minutes or hours, but like, within a reasonable amount of time, this model is solved. Same now if we then start to plot, for instance, the consumption as a function of the different shocks that we have, like at the beginning is complete nonsense. Then the cost function on the left-hand side goes down and you see the consumption start to look reasonable. And then what you see here is also what I plot here is the relative Euler error over iteration. So you see when you look at the different age groups, the error goes down. So like here it's somewhere here, then it goes down just below 0 in the log 10, goes down, and so after reasonable amount of time, the average Euler error is on a reasonably low level. And again, so this you can solve on a laptop, which is, I think, pretty cool. And as I mentioned to John before, I spent so much time with sparse grids trying to solve these models. One advantage, which I really want to insist on, is like you completely get rid of, like you don't need to get a solver to solve your optimization problem or your nonlinear set of equations. It's you use the stochastic gradient descent. Yes, that's true. But like for those of us who work with Chebyshev polynomials or sparse grids or so, like if you work with a hard model and then at some point the solver doesn't converge, your entire construction kills the approximation. So you need to do some tricks. So in particular, if you solve an optimization problem which is right at the kink, it's a non-convex optimization problem. So the solver often does spooky things. So this is really cool. Here you just simulate and use the stochastic gradient descent. You don't have to worry about the equations too much, the equation solving too much. And then with that, obviously, as I said, you can start to with the borrowing constraint, or you could think of all sorts of other exercises. You can start to study, how lifetime consumption changes if you change the borrowing constraint, and then you can start to do policy experiments. So that's the basic idea. And as I said, all of the deep equilibrium nets is online. The key here is really neural nets combined with simulation, combined with an appropriate cost function, combined with the proper network architecture that encodes your problem, can do quite cool things. And in the paper, we also look at a model with a continuum of agents. So the concept is pretty cool. Now let me skip. Yes.
A couple of questions. Okay, I think John answered just the one of, but that leaves the one of Juan Pantano. So could you also use these nets to solve discrete choice models where optimal policies are not defined by the first order condition being 0? Or does it only apply to continuous choice models?
No, you could. I mean, you need to think a bit how, but like if you, so if you think of in discrete choice, it's similar like a classification problem. So what I would then have on the output node, I would then have a bunch of, so that the policy functions that you would have is a function of a discrete state and a continuous variable, right? And then you would then solve probably you would use two networks, probably one for a default and one for a non-default, or whatever your choice is. And then you have the two networks that approximate the respective states of the world, and then you take the max of the two. I mean, there's ways of that, but I would then look into the neural nets are very good also in classifying. And classifying is nothing else than a discrete choice, so to speak. So, well, yes, I haven't done it, but I'm really optimistic that this should be possible to be done.
And sort of my question as a more empirical guy would be from the data side. So you at some point said data should be 10 times the size of the parameters. Is that the parameters of the neural approximately?
Yes. Yeah, so this is just this a hand waving argument. So the thing is, you know, for instance, polynomials or so, they're data efficient. So you need little data to have a good interpolant. Neural nets, they tend to be completely overspecified. So you need a lot of training data. And this is why we here, so let me be a bit more explicit. So, you know, this is the typical, you know, max U plus beta. So X. So the typical Bellman operator. So typically, when you solve you know, a dynamic program, each of these equations, they're very expensive to generate. This would be in the language of neural nets, that would be supervised learning. This is a problem for neural nets because, as I said, you have a lot of parameters in the network. So if you have like a 7-layer, so we have this in one of our examples, you have a 7-layer, 7 hidden layer neural net, you have like 1 million parameters. So you require some sort of 10 million of observations. So this is expensive if you solve a maximization problem for all of those. But the thing is, when you do simulation, generating, you know, we generate here for these OLG models, even on a laptop, billions of observations. So, so this is not what you have as an empirical guy. I'm not talking about, you know, like your the how I say, the parameters that you want to match. I'm just talking about the weights in the neural net. It's just like you have a lot of those, and to compute them, you need quite a bit of data. With the estimation, give me 5 more minutes, and then you will see rather what I mean there. Is that okay? Okay. And so I'm skipping the parallelization. As I said, like the stuff that we did so far, it always worked on a laptop or potentially on a laptop with a GPU. But there's also ways to, you know, if you really want to go crazy, you can also put it to clusters. So we scaled it up to 512 GPUs with orders of magnitude speed up. This can be done easily. Now let me just the last few moments also, you know, move towards estimation. So that would be this paper here, and I will not do it. I will not give it fair. You know, I will just like go over the basic idea. So now we know how to solve a very complex model, and we eventually would like to confront it to data. Now, the basic idea, if you want to do estimation or calibration or uncertainty quantification, is, you know, you always have essentially, for instance, say some empirical moments that you observe, and then you solve your model in a loop until you restrict your parameter to where it should be. And this can be very costly, because sometimes if you look at the literature, you know, I know there's some papers by Tony Whitehead and others. They use sometimes hundreds of thousands of model evaluations until you have good estimates of the relevant parameters and statistics. Now, this is obviously these days, when you have very rich model specifications, this is an unsatisfactory situation, because this would then mean, okay, just impossible, or like just very, you know, cumbersome to do that. Now, so what you do in this paper, but like it in the context of option prices, and just like because option prices, because you have a lot of them, it's easy to showcase that the method works. So the basic idea now is just we replace the economic model with a so-called surrogate. And the surrogate, let me just move a bit forward. A surrogate is essentially just like, just imagine I solve the model again as before, as a function of my endogenous states, my exogenous states, and parameters. And now this comes back again to the question John had before. So for the parameters, So like the endogenous and exogenous state, we use like obviously the model dynamics and the dynamics implied by the policy we're solving for. For the parameters, we don't have this thing. So what we do for the parameters, we need to assume, first of all, like a range from which we are sampling from, and potentially even the distribution. But what we do, in fact, is for the time being, we just use a uniform distribution for the parameters at hand, because there's like the entropy, this entropy maximizing thing. So if you have no idea about the parameters and the distribution, we just take them uniformly distribute. So what we do is we solve the model as a function of this extended state space. And again, we do this with neural net. That means again, we don't need to approximate the high dimensional object on a Cartesian grid, but it's essentially, it can be of any geometry. So it's just by sampling / simulating, we approximate the solution for a model. And now once you have this surrogate, it's like a lookup table. So I can super cheap, let me just move forward, then I come back again. So when I want to estimate parameters, so I say I have an empirical moment that I observe. So instead of needing to solve my model repeatedly, it's just an interpolation of my model. It's just an interpolant that I confront with the true data. And that's it. And this is obviously super cheap. So you can take any, off-the-shelf optimization routine, and you get your parameters. Yes, and so something else which probably, I cannot do fair credit here. It would require a bit more time. But also, remember, since we're simulating, so I was just saying, the output typically would be a policy. So the output could be the policy given states and parameters. But you obviously, because we simulate, you also have moments. So when you solve the model, you get also the moments for free. So when you then also have them as an output, you can have the solution of your model, the policies, but you can also have the moments. And then once you have that solved, you just do your post-processing with this lookup table, and then you get your optimal solution. And then the last cool thing, and then I'm done, is for most optimizers, you need gradient information. And again, because you have the neural net here, you get that for free. So you can really estimate complex models relatively quickly. And then just like to make it the example, so here we estimated an option pricing model with 13 states. So it had essentially 8 parameters that were relevant. If we would, so we did the exercise. So like we used a tuned library, a quantlib, and then we did a bunch of exercises. So like to solve the model in the classical fashion, it would take 125 hours, but without deep surrogate technology, it would be just 0.2 hours. So this is pretty cool. And you see, like the parameter estimates, so there's almost no error. So I mean, here it's obviously it's a model, so we could simulate the data and compare, against the true solution. Yes, so before I'm stopping here, and sorry for taking a bit too much time. So with this technique of this deep structural estimation, so there's a pro and a con. So the con is you need to solve your model once. So you need to generate this surrogate model once. This can be potentially a bit expensive. But on the pro side, you only have to do it once. And that also implies is, so for instance, for these option pricing models, this is probably less relevant for you know, other macro models or whatever. But in the context of option pricing models, there's a limited amount of these models. So essentially, you can generate, you know, for all these option pricing models, you can generate the database, you upload it, and then someone else can recycle it for whatever study. So in that sense, it's nice. And then just like to make the example, so if you would again use like the standard naive, you know, grid techniques to estimate, this particular model would have used, you know, almost a million gigabytes of storage, while in the end of the day, once we had our surrogate model trained, it was only 20 megabytes. So this is also pretty cool just from an operational point of view. So I can send this model around, you know, to any referee if he doesn't trust me, while you know, this raw data is kind of an operational thing to use, not speaking of well, computing it. So you know, I know like that was a bit too fast at the end probably, but I think you got the basic idea. So comment one, so neural nets are super useful in econ, but I believe one shouldn't use them like in the most naive way. One should think a bit about how much economics can be encoded in the architecture and the loss function, then they're really effective. And point two is not only for solution, but also for estimating. So combining the two provides a lot of, well, interesting avenues for carrying out research. And yes, so I hope I didn't kill you on a Sunday afternoon with speaking way too fast at the end. But yes, so is there questions or comments?
Everybody looks still very much alive. No worries. We've trained everybody well and ourselves well to make it through long days.
Good, then thanks for that.
So no worries. Well, the day has been long, not your talk.
Yeah, I can believe. So I already said to John, so two comments, like also like if someone wants to have like you know, office hours or so, because I'm physically not there, you know, he or she can send me an email and we can have a discussion over Zoom. So that, you know, I would be happy to accommodate that. Then comment two, just like you need to play with codes. So like I think the basic idea is clear, but like what you need to do is just get your hands dirty and experiment. And then like after the fifth failure, it will start to work. Is there questions now?
So just two questions. This is Bertel. Okay.
Yeah, hi Bert.
I'm over here. So yeah, okay. So I'm who? What are the convergence properties of this? Is it always working, or do you have to be lucky? Okay, that's one thing. And then the other question, that is, could you impose the objective criterion from the from you know, the sample criterion you're using in estimation, or say derivatives of that, like the scores if you do maximum likelihood, as part of that loss function, and do the whole thing in one go?
So the first question is like, you know, that's why this paper was written with 2 PhD students. So stochastic gradient descent should actually be called student gradient descent. So because you know, does it always work? Once you have the good architecture for your problem, it works seamlessly. But finding a good architecture, that means, you know, finding you know, what sort of activation functions that fit your problem, or you know, so for instance, what I did not talk about, so feeding in redundant information. There's all sorts of tricks that help. So like convergence properties, this is a tricky question, as you know, in general, right? So there's, when you use time iteration as an example, you know, you don't have a convergence guarantee except for very few cases, So like from the neural net's perspective, I can always approximate anything, you know, relatively well, but I could end up in a local optimum, not a global optimum, which completely misspecifies my problem. So in that sense, that comes back to what I said earlier. You need to really, you know, do ex post verification. For instance, like, you know, you simulate, you know, you take the out of sample error, or you know, you simulate, you do all sorts of checks. But yes, if you, for me, in 6 complete different projects, going from you know, from climate economics or overlapping generations models, or like an international trade model, or these option pricing models, they always work, but the you know, like it takes sometimes a bit of nerves to get there. That's why student gradient descent. So and then the second thing, what you said, yes, clearly. So you can have that thing also self-calibrating. So that's the cool thing. So I didn't talk about this so far. So when you simulate, you know, just to come to your likelihood question, but let me take a simpler example, and then this will answer your question probably in a more clean way. So imagine you know, you have your loss functions, right? But you also simulate always a path, say 10,000 steps. So if you track now the moments implied along your simulations, and then you add to a cost function, you know, the moment that you're simulating, you know, you approximate that as a policy on the right hand side of your neural net, and then you take as a cost function side the moment, you know, which is represented as a policy minus the true moment, and you have parameters which the neural net can use to adjust. When it solves into the calibrated model directly. This you can do.
Very cool. That was essentially my the answer to my question. Yeah. So I was thinking.
But also, so I did that in some DSG model at some point, just to be, you know, like you need to be a bit careful here with tricks. So what we did in the end of the day is like we added a pseudo state / policy where we had an exponentially weighted. I mean, you know, we didn't want to keep track of all these 10,000 points, then compute the moments. So we took some exponentially weighted thing to make it computationally more feasible. But like, I guess you get the idea. So it works if you do it. But like the devil is always in the detail.
Excellent. Any other questions, Fedor? If you want to, sure.
Hi, Simone again.
Hi.
So I love your last slide, which says keep calm and accept the fact that it is over. It's also, it was nice to see that some expert knowledge is still needed for this, the set of parameters that would be useful. And I guess you can come up with the argument how to try to figure it out automatically. But my question is really, have you thought of the situations where, as an expert, I set up the model which admits multiple, and even not thinking about the parameters, but for.
So Fedor, sorry, I didn't hear now half of the question.
Oh, okay. So the question is, can I work with the deep neural equilibrium framework with dynamic games, which, as we know, may admit multiple solutions?
That's an unfair question. I wouldn't know how to do it off the shelf, honestly. So the thing is, this is designed to find one equilibrium. I wouldn't know. So just like to. No,
You need one PhD student per equilibrium.
No, so in a DSG model, once we had multiple solutions, and this caused problem because the solver jumped around from one to the other one. And now in your cases where you have, like, I remember your paper where you have a gazillion of different equilibria, I wouldn't know how to do it. But it's just my lack of non-knowledge of these models. So sorry, no good answer here.
Yeah. So I don't think that's a wonderful answer. We think that was a wonderful talk, and this now concludes the conference. So let's give Simon another hand.